What is going on, guys? This article is a little bit old, 2019, but it's a really, really good, well-written article. Yves Trudeau, well done. That's a very good article discussing UUIDs are popular but bad for performance. Let's discuss. That's the title of the article. I'm gonna prefix this that there is some misconception here that I'm going to talk about at the end of the video. But here, Eve only discusses MySQL, obviously, and the specific architecture of MySQL when it comes to the random nature of UUID can screw you over. So let's go through it. So I'm going to go through the parts of that I'm really interested in, and then jump through the stuff, the article. I'm going to reference it below for you guys to read it at your leisure. So what are UUIDs, or universally unique identifier? I usually refer to them as GUIDs, globally unique identifiers. I don't know if there, honestly, if there is a difference or not. There might be, but this is how they look like. Very, very useful, guys. GUIDs and UUIDs are very useful, specifically if you want to build an idempotent backend API such that the client is responsible of submitting row inserts or orders. And you want to make these post operations or these writes idempotent. That means if the client had to repeat this somehow, it has a failure, it can safely repeat the same operation without a side effect, essentially. Very, very important idempotency. I talked about it right here. If you want to learn more about it, Kafka implements something similar to this to achieve idempotency. UUID is one of the most popular things to achieve that. Obviously, it's used a lot in other ways to guarantee the uniqueness, because you don't really get the chances to get a collision is very low, right? There's the details of how Yves going through the details of how you build a UUID. We're not really interested in that. We know how it works. So what is wrong with UUID value? Let's read a little bit and then discuss. In order to appreciate the impact of using UUID values as a primary key, and that's the discussion here. We're using UUID as a primary key, and not just a primary key. We're using it as a primary key in MySQL because it's a very different thing. A primary key in MySQL is completely different than a primary key in Postgres, which is literally, there is nothing called a primary key in Postgres, right? It's always a secondary key, right? And we're going to talk about that. Clustering concept of this really is the key, or as Oracle calls it, that's my preferred name, index organized table. It is important to review how AnnoDB, which is the default database engine for MySQL, AnnoDB stores the rows of a table in a B tree for the primary key. In database terminology, we call this a clustered index. The clustered index ordered the rows automatically by primary key. So the table is organized based on the primary key index, right? So think about, like, if you have a primary key with a value of 1, the entire row exists next to the index, next to that value, and so on. Value 2, the entire row next to it. There is, unlike Postgres, where the heap exists somewhere and the index exists somewhere, and there is a pointer to that thing. It's slightly different. Okay, clustering has advantages and disadvantages when it comes to that. Obviously, you have everything tucked nicely together and ordered because they are literally an index, right? So they are ordered. The table is ordered. Okay, focus on the word ordered here. When you insert a new row with a random primary key value, okay, AnnoDB has to find the page where the row belongs, load it into the buffer pool. If it's not already there, insert the row, and then eventually flush the page back to disk. With purely random values and large tables, all B-tree leaves pages are susceptible to receive the new row. There are no hot pages. Because of, I'm going to explain this in a diagram that I drew in a minute, but essentially when you draw, everything is, in a clustered index, everything is grouped together. So if you pulled one page, you have all the rows in that same page. So technically, if you want to write row number 1 and you just pulled the page and you want to write row number 2, that page is already there. You just slice it right in the memory, and then you do 3, 4. It's all tucked into that same page. But if you're inserting row number 1 and then row number 100 and then row number 7,000 and row number 8,000, these are different pages. So imagine the reads that happens. And you might say, Hussein, the UUID is not really a number. It doesn't matter. This exactly happened with any random thing. It doesn't have to be UUID. And that's the misconception that I think is happening. Yeah, when you have UUID, obviously you have randomness, but you can't technically have randomness with integers, right? Your client could be submitting your primary values if it's not sequenced, right, as a random values, and you get the exact same behavior. In order to explain this better, let's go to my, I drew something quick and dirty here to explain this. Let's go through this and try to explain it here. All right, guys, how about we take an example of how this actually works instead of just reading. So I drew a few diagrams to explain this. Let's assume this is my memory. This is the clustered index. These are called pages, and each page has a specific size and it can hold n number of rows, right? So let's say for simplicity, it can hold 10 rows, okay? And since it's clustered, it has to be ordered. So page A is row 1 to 10, page B is row 11 to 20, and so on, okay? So let's go to an example where we're gonna do a sequential write. So 1, 2, 3, 4, 5, beautiful, nice, beautiful sequential writes, one after the other. Let's see the effects, and then we're gonna do random writes and see the effects on MySQL, or a clustered index, because you can do clustering in Postgres as well. But it's not on by default. So now if I'm inserting row number 1, the ID field number 1, which is the clustered index, that's the ID field, and say, okay, the database will ask, okay, row number 1, which page is this? Very quick check to see that, oh, it's actually page A. You can it's a very quick mathematical algorithm to find out which page. And then once you find the page, you pull it from disk, so that's a read, seek on disk, pull it in memory, and then the next step is we write the row inside that page, making it a dirty page. So we just touch this page in memory. And you might say, Hussein, we're touching the stuff in memory? How about we need to write it back to disk? Otherwise, what happened if MySQL crash? Don't worry about it. There is something called the binary log, or it's called the wall, right? The write ahead log, where things are written to disk in an append only mode, just in case of a crash. But don't worry about it. So in case of a crash, this can be reconstructed. This is out of the scope of the video, but assume that we are durable. This is an ACID database after all, right? So I wrote this. It's a dirty page. So I read once, and I wrote to the memory, not so bad, and I written to that page. Let's write now row number 2. What will happen? The database says, okay, where is row number 2? Row number 2 is also page A. Well, wait a second. I don't need to go to the disk because page A is nicely available for me in memory. So all I have to do is just write number 2 in that same page. So just write it. So that's a quick, beautiful, fast write. Okay, let's do about 3. Same thing. 3 is also there. 4 is also on the same page. So I didn't do any read to the disk. It's all beautiful writes to memory. So it's so fast. Okay, up until I reach page number 11, page A is full at this time, right? So the MySQL at a certain time, it will decide to flush it to disk, right? I'm not going to go through when exactly, because that's 3 or 4 parameters in MySQL to configure when to flush it to disk, but assume that A is now flushed. But now I want row number 11. I want to insert row number 11. Oh, it's in page B. So I'm going to do a read and then into the disk, pull it to memory, write my row 11. If I've row 12, same thing. It's nicely available in memory. Do thing 13. You see the idea, right? So now this is what happens when we are in sequential. What about random? That's the UUID, the GUID case, where every single value, the primary key, is completely random. It's not sequential. So let's take the same example, but as integers, because it's the same exact problem. So I'm going to insert row 1000. Okay, row 1000 is page P. Let's go ahead and pull it to the memory, write it. And then the next row right is row number 1. Oh, row number 1 is A. So I'm going to read and then pull it in memory and then boo, do that. Not so bad. It's still, because it's one read and one write technically to the memory. It's not that fast. There is another write to the binary that I'm not showing here, but we don't really count it here. This is what matters here. Now the next one is 20, completely different page, PHP. 50, completely different page. We're not reusing those beautiful cached dirty pages. Unfortunately, they're just sitting there. It's so sad when you see this. It's so sad. It's an insult to the database. Let's go ahead. What happened? My memory is full. My buffer pool is full. What will happen to the next write? The next write is 80. And guess what? Well, 80 is K and it's not in the memory. So I have to read it and I have to write it to the memory, but oh, it's full. What to do? Go and you are obliged to flush some of the pages to disk. The old, recently used pages, based on the caching algorithm. So now the buffer is full. Oh, let's just go ahead and flush P. So we're gonna flush P, read, first of all, read, try to get it from memory, flush existing P, and then put K back. So you just did a read and a read in memory, and then another write. All because you want to do a write. And then if you want to count the write in the binary block. So you did a lot more work. And that is the graph that I'm about to show you in Perconas. When you reach this stage, when you like essentially thrashing the memory, just flushing back and going back, flushing back and going back, you are essentially becoming IO bound, they call it, right? When you are in memory, when you have enough memory in the pool, that's fine. I mean, yeah, you can just put a lot of memory and solve this problem, but you're just delaying the inevitable. Let's go ahead and do another one. 500, another page. If you happen to hit the same page, which is very rarely in a GUID environment, you'll hit the same dirty page. But if not, then you're gonna always do this: read, read, write, read, read, write. So guys, let's go through the graph. I want you to pay attention to these three types here. So what Eves did, he stored the GUID values, the UUID, as a string, 36 value, or as a binary because they are 16 bytes, right? Or as a base 64. He tried three approaches. And look at this. When you first start, let's take the string example, right? When you first start, writes are like you have like 8,000 writes per second. So beautiful. And that's when your memory is not full yet, the buffer pool. Once you hit that, reach this threshold, after what, 150 seconds, the memory is now full of dirty pages that are barely used. The insult to the database, right, that we talked about. It's just like, yeah, you have all these pages with a single write in them. Ugh, so sad, so sad. At this point, you'll start flushing to disk. So an insert is doing a read and a write. Two write, essentially, like if you think about it, to the binary log, right? So you're doing more work. And if you're doing more work, your throughput just slowed down. So you can see that just dies. All of a sudden it comes back to here. Because now the thrashing becomes like you're flushing back from memory to disk, from disk to memory, right? And now you might say, Hussein, when he did a binary 16, we went a little bit longer. Why? Because the size of the UUID is smaller. So now you can fit more writes. You can fit more dirty pages in memory, essentially, because the size is so small, right? That's the beauty here. So, but still, it's inevitable. You go a little bit further, but eventually you're gonna hit that memory limit, and Eve beautifully explains it here, right? Explain. Let's read through here. In all cases, the insertion rate is at first CPU bound, the memory. When you talked about, like, we only read from disk the page, and then we put it in memory, and then we write to memory, which is now at this point we're just CPU. We're just using the CPU, right? But as soon as the table is larger than the buffer pool, the insertion rapidly becomes I/O bound. This is expected and should not surprise anyone. The use of smaller representation of UUID value just allow more rows to fit in the buffer pool, but in the long run, it doesn't really help the performance. So he suggests here two solutions, and they're beautiful solutions. I like this better. So he said, okay, since UUID are random, let's introduce some sort of order to them. So some sort of sequencing. So what he did is essentially he, at the first 4 characters, he tried to fix them based on the current week. So they will be exactly constant. And when they are constant, right in the first week, as you come first week, they will all become part of the same value. And as a result, the database will say, oh, these are very nicely almost organized together. So the database will look at this as they are synchronized sequential writes, and as a result, you see the first case, right? So he did that part. The other part is he's just mapping UUIDs to auto-increment integers, right? So let's not use the UUID as the primary key. Let's use the primary key as an integer that is sequential, not just any integer, because you can just still do random inserts in an integer. You have to be auto-increment to get to be useful, right? And let's not manage it, right? And then use essentially a mapping table to map the UUID and check for duplicates and all that stuff and map it to the integer. So guys, this is very interesting, right? And he's showing that, okay, the pseudo order, all of a sudden, look at that. Using the pseudo order, you can see nice approach, beautiful, nice approach. So let's end this article, guys, by discussing Postgres, because Eve didn't mention it here. But Postgres, compared to MySQL in this case, takes the advantage, in my opinion. And I might be wrong in some cases. Correct me, guys, if experts out there. Postgres does not use clustering by default. It doesn't have a clustering. So you create a table, is not clustered like MySQL, right? MySQL, you don't get a choice. It's always clustered by the primary key. So you have this behavior if your primary key is a UUID. But in Postgres, you can create the primary key, which is just a secondary key, right, which points to the raw directory. It just happened to be unique, right? And when you do that, there will be no any problem, because the table is not really ordered. And new inserts is always going to go to the bottom. It's not ordered, right? It's not clustered. So all the writes are going to the bottom. It's not like the database has to go, okay, oh, this has to be going this page. Oh, this has to be, because it needs to maintain order. Even, that's being said, that's with the default Postgres. Even if you did cluster in Postgres, Postgres does not maintain order in a clustered table. Yeah, I was surprised too when I read this piece of information. Clustering is a one-time operation. When the table is subsequently updated, the changes are not clustered. So inserts are always fast in Postgres. They're not going to go into the right place. So you might say, Hussein, that's not really clustering, is it? It's going to cluster existing data, but new changes, new updates is just going to go to the end. So you don't have, if Eve did the same graph, it's not going to look the same. It's going to go, I think it's going to look just straight, because there's no problem with that. But if you do want to cluster it, you just call recluster. I think that's what it's called, the command. Just call cluster again, right? Calling cluster will recluster the index. And when it recluster the index, it will reorganize those rows and tuples back to the place where they should belong, right? Essentially, this is the whole thing is just very interesting to me. Very well written article. I'm gonna recommend it below, guys. Guys, what do you think? Do you use GUIDs in your tables? Let me know in the comment section below. I'm gonna see you on the next one. You guys stay awesome. Yeah, good article. And by the way, guys, if you don't follow Percona, they produce high quality content in blog forms and on YouTube channel. Check them out. They talk about not just MySQL. They're specified in MySQL. If you've noticed, most of the article MySQL, Mongo, benchmarks, Postgres, MariaDB. If you're into this stuff, check them out. I'm going to see you on the next one. You guys stay awesome. Goodbye.